Good afternoon, everyone. So, I am Dr. Saravanan. Thanks for the great introduction. So, I am an assistant professor at University of Texas Tyler and then adjunct faculty at University of Texas at Dallas. So, we are going to today in today's talk, we are going to talk about the part of my DOE funded project in collaboration with the Lawrence Berkeley National Lab, which is funded by DOE Oscar Fair Funding Award. So today's title for our talk is going to be accelerating IO in scientific workflows with the impact of in-memory computing or in-memory file systems. So could you please go next slide, please? Okay. So the overview of the today's talk is as I mentioned, this is part of my DOE project. So wherein we would like to find the solution for the HPC and AI-based storage-driven solution, wherein we would like to integrate the multimodal data, which comes from the different types of the data sources, which consist of the different types of the layers. So as we all know that the HPC systems itself is facing a significant bottleneck if we have the heavy workloads. When we started off this project, we started off with the NWK molecular dynamic data and then OCP data sets. So compared with the OCP data, the molecular dynamic data sets is a little bit smaller, but even with the higher or heavy IO workloads and then random access patterns and then analysis demands, which is obviously going to degrade the simulation as well as the analysis. So what we try to achieve is through this project, we would like to minimize the IO latency, and then we would like to go with the storage driven solution based on the HPC and AI. So for that reason, we just take the use case like the molecular dynamic data with the NWKM data set, which is going to generate the vast data sets, which consist of the thousands and tens and then thousands of frameworks, as well as the billions of atoms at the same time, also which has the billions of coordinates as well. So if you consider the traditional storage solutions, which is the disk IO, which is critical, become the which is going to degrade the performance based on while performing the simulation as well as the post processing. So this is the huge challenge which we faced when we worked with the molecular dynamic data sets with respect to the NWCOM simulation. So the challenge, as I mentioned, is like a high IO latency, as well as the limited scalability and then resource inefficiency from the high CPU memory, as well as the which slows the disk access. The core problem which we would like to solve is can we eliminate the IO bottlenecks in scientific workflows by moving from the hybrid solution called the in-memory as well as the IO integration. That's part of this data pipeline. So in this project, the DOE project, we have the different kinds of the layers, data acquisition layer, then storage layer, then after that, the utility layer, and then after that, data learning layer. This is this part which comes under the data storage as well as the utility layer. So the main goal for this part is how we can provide the solution with respect to the hybrid IO as well as the in-memory computing solution with respect to data storage. Could you please move next slide? Yeah, so the motivation why this work matters, right? As I mentioned, there is a problem with the HPC bottleneck. So the HPC simulation, as we all know that the HPC workloads which generate the massive data sets. So most of the time we face the 70% of the time we are spending on the execution time on the IO operations, right? So this is going to limit the simulation performance as well as the throughput, right? At the same time, the traditional file system like Lustre, HDFS, SEP, and all, which is very heavily rely on the disk-based storage and then high latency as well as the limited throughput. So the disk IO also becomes the performance bottleneck when we are moving from these small data sets to the large data sets, which we face the problem when we we stimulated with the molecular dynamic data set with the 1H90, which is a little bit of complex data structure, and then 1FME, so which is the larger protein folding data set. So that's what in the disk-based IO becomes the becomes the performance bottleneck when we are moving from the smaller data set to the larger data set. As well as when we are looking at the HPC workloads, so we have the problem of rising demands of the scientific workloads, right? So we need to have the low latency as well as the high throughput with the IO solutions. And then when we were discussed about the traditional way of approaching the IO bottlenecks, how we can improvise the performance, how we can improvise the latency and all. So we just go with traditional file system, and then we came up with the solution called the hybrid in-memory computing with the IO integrations. That's the reason. So we found out the solution called the in-memory file system, which is the Apache Ignite. We just leverage the service called the Apache Ignite's in-memory computing, which is going to reduce the delays as well as the responsive time. So why we need to go with the Apache Ignite? So when we did the literature survey, so we found out that which is the Apache Ignite, which is the which is the native persistence as well as the fault tolerance as well as the high performance as well as the scalable. So that's when we would like to integrate the in-memory computing file system with the in combination of the IO integration. So this is little bit about the background about our work. And still it is the immature state because we just started our project, so we would like to explore more in future. Yeah, go ahead with the next slide, please. Yeah, so the key research areas we would like to, in this talk, we would like to compare the in-memory file system like, IDFS Apache in-memory distributed file system against the disk-based IO for the larger scientific data sets. And we will also assess the efficiency for the IDFS using the data-intensive operations. And also we would like to assess the performance of the based on the read-write operation of the collected molecular dynamic trajectory data. Next slide, please. Yeah, so the related work, as I mentioned earlier, so we just did the literature on the Luster, which is high throughput but the disk-based storage, and then HDFS, which is good for the fault tolerance but slow in writing operations, as well as the SEP is versatile but which is also disk-based solution. Then Apache Ignite, which is no native storage but which is compute focused. But if you go with the in-memory computing with the Apache Ignite, which combines the compute as well as the storage in RAM. So that's when we would like to leverage this, features and with respect to the in-memory computing systems of Apache IDFS. Yeah, next slide, please. Yeah, the proposed solution. So as I mentioned, we were proposing the hybrid solution of Apache IDFS with the integration of IO integration. So why it is going to fit with respect to our scientific workflows, as I mentioned, like, which the IDFS system, which is going to speed the read and write operation for the large scale simulation, as well as the minimal CPU memory usage, and then built-in function for the fault tolerance as well as the native persistency. So that's the reason we just would like to go with this hybrid solution fit for our scientific workflows. Next slide. Yeah, the experimental setup, all the preliminary works we set it up in the NUX Perlmutter at Lawrence Berkeley National Lab. And then right now, we just limited with a single node Ignite setup. And then we just use the transactional partitioned in-memory caching. So yeah, next slide. So the data set which we used is 1H90. So initially we performed with the synthetic data. And then after that, we just go with our 1H90 and then 1FME. So these data sets, or if you compare the data structure nature, this is the little bit complicated data, but if you consider the 1FME data set, which consists of 226 to 83 frames as well as the 504 atoms per frame. So each frame consisting of the XYZ coordinates as well as smaller data set compared with the larger and then complex data set nature as well. We also performed the operations of sequential, random, and then concurrent writes. And then we measured the throughput metrics called the throughput latency and then CPU memory behavior. So yeah, next slide, please. So this is the results which we obtained from the two different data set, 1H90 and then 1FME. So 1H90, so read operation, so write throughput is like one small like a 625 and then 1FME is 722 large data sets. So despite of the massive, if you look at the data set nature, if you go back and then see the previous slide, so the data set is massively scaled up with respect to the 1H90 compared with the 1FME, right? So 1FME massive scale up is happened, like the frame count is approximately like 174 times huge than the 1H90. But irrespective of the massive scale ups, the throughput scales up well. So in fact, if you look at the 1FME, so it performs slightly better than the 1H90, which shows that in-memory framework scales up well, right? And then if you consider, next slide, please. Yeah. Yeah, this is the metrics which we collected from the two different data sets. So first one is the write operation and then read operation. So the write throughput, if you look at the diagram, so which is compared with the 1FME, approximately 15.5% greater than or larger than the data set, and then average write time, if you consider, slightly better than the increased framework, maybe based on the the overhead. At the same time, if you see the CPU, I think, like, could you please go to the next slide, please? Sorry, yeah, this is the one I'm talking about. Sorry about it. Yeah, so if you look at here, the total frame size of 1H90 is 151 and then 284, which is slightly higher scales up. The frame size is more, and then average write time per second is also compared with this one, so slightly better to the right latency when you are increasing the frames. And if you look at here, the CPU usage during the write is also rises because of the data set increase, right? But it is also a little bit manageable. It's not that very huge amount of the CPU usage. And then if you look at the memory usage, the memory usage is consistent with respect to 8 and then 7.5, which is effective allocation of the memory, which uses the fixed buffer sizes. And then this is with respect to the write operation. So the write pipeline scales effectively with the minimal latency. If you look at the diagrams as well as the metrics which we collected through the NWChem and then different data set. And at the same time, if you see the CPU usage also rises as expectable because the data set is increased and then the frame count also increases, but which is also manageable. And the stable memory usage is good with respect to the buffer size reuse as well as the memory strategies. And then after that, the read performance, also we compared the read performance. So the both read throughput, the previous could you please go back to the previous slide, the read throughput? I would like to show. Oh, yes, correct. So here, the read throughput is also, both areas is showing the high consistent read performance. and then average read time per second very slightly increased in the read time, which is also negligible. And then CPU usage also very scales proportionally with the data volume, because of if, as we all know, that if we increase the data size or the frame count, which is also proportionally increasing according to the data volume, and the memory usage, suggesting that we have the little bit of the, if you look at this memory usage 8 with respect to the 1H90, and then the 1FME is like a 7.50. So slight dip in the higher or the larger data set, which shows that there is a slight dip, which is going to suggest us that there is the optimized catching solution for the larger data set. So on the whole, if you look at the read and then write performance, the Apache Ignite or the similar tools handles the, could you please go to the next slide? Yeah, sorry. Next slide, please. Yeah. Next slide. Yes. So in the performance observations, so the in-memory architecture drastically reduces the I/O overheads, as well as the it handles the large scale ingestion as well as the retrieval efficiency. At the same time, there is no increased bottleneck with respect to increasing the workload. So when we compare with the 1FME and then 1H90, but still it is in progress state, work in progress state, but we would like to go and then do with more use cases with respect to analyze the different kinds of the metrics. So that's when we'll completely understand the CPU usage as well as the memory concept and memory utilization, and then optimization techniques in future. At the same time, you can also scale more with respect to the larger data sets. So yeah, so which achieves the in our whole results, we observed the few things about the different smaller versus the larger HPC workloads, as well as the scientific data sets like 1H90 and 1FME. So which achieves the high throughput and the low latency with respect to read and write workloads, and then which is also ensures the resource utilization with the low CPU and then manageable memory demands, and also which supports the complex queries and then operations within a single node setup. Yeah, go ahead, next slide. So the limitation, as I mentioned, like we just start off this project, so we have simulated our works, and then we just tested our results with the limited synthetic data. First we went with the some synthetic data we generated, and then next we went with the in the 1H90 and then 1FME only with the single node tested, which is not evaluated fully with respect to the distributed capabilities. And then there is no direct benchmark against the Lustre HDFS, and then in this paper or in this work, we need to have the more assessment in order to analyze the scalability, overhead, and then resilience. Yeah, next slide. So the conclusion is like in-memory architecture is enabled with the real-time read and write operations, and then Apache Ignite proven effective for the large-scale simulation data, also which is also giving the low latency, high throughput solution with minimal. Next slide, please. Next slide.
Can you restate?
Next slide, please. Can you hear me?
Can you restate your last bullet point? You broke up a little bit.
Oh, can you hear me now?
Yeah.
So the conclusion is like, yeah. So the Apache Ignites, when we compare with the two different data sets and along with the synthetic data, we achieve the low latency, high throughput with a minimal overhead. That's what I mentioned. Yes.
Okay.
Yeah. Go ahead, please. Yeah. So in the future work, as I mentioned, we already set it up with the multi-node already planned, and then we would like to compare with the Lustre and then different traditional workloads using the traditional benchmarks like IO and then IO 500. And then we would like to integrate with the real world scientific applications as the labs and all. And then as well as we would like to improvise or boost the faster time to solution and the lower checkpoint overhead and improve the interactive visualization for the HPC performance and the usability. So as I mentioned initially, this is still in work in progress. So we have to go with the larger data sets. So as well as when we started this with this DOE ASCR project. So initially we struggled with the real-time change point detection. So if you consider the data set is the static data set, then we will be able to find any kind of anomalies or any kind of a change point occurs in the system. So any kind of a system, right? But when we are dealing with the real-time data sets, so which consist of when we collected the NWK molecular dynamic trait data, which consists of the XYZ coordinates, we don't have the reference point to analyze the change point when it is going to be occurred. So that time we find the bottleneck with respect to we would like to go with the real-time solution for the change point detection. So that's when we came up with this idea of how we can leverage the real-time analysis with respect to the storage-driven solution. So that's what we would like to go in future, and then we would like to test our use cases with the multiple use cases. Right now we are just using the only the NWChem, which is the computational chemistry simulated data, which is going to give you the molecular dynamic trajectories. In future, we would like to go with the
Hello? Is she still connected?
Wi-Fi is still working.
Okay.
And Zoom is also running, so.
Is she still on
Oh,
the...
no, for whatever reason I was kicked out.
Oh.
That's strange.
Sorry.
No.
I don't see her on the Zoom.
Yeah,
Do you see us actually? Okay. So it's not on our fault, on our side, right?
No, it's just, I'm in me and
Yeah,
you, so.
okay, so
Okay.
we lost her.
That's pretty close.
Anyone wants to pick it up from the same?
We still have 5 minutes for our next speaker, so oh, she's
Back.
she's rejoining.
Yeah,
hi. Can you hear me now?
yeah.
Yes.
Sorry, I am in India. There is a sudden power cut here. Sorry about the inconvenience. Yeah. So will you be able to hear me now? Yeah. Hello.
Yes.
Yes, okay. Yeah, the future work, as I mentioned, we just tested our results with the NWChem data. So when we started with this DOE funder project, so initially, if the data set is static in nature, we will be able to analyze them with respect to if there is any anomaly happened or if there is any change point detection happened or no. So, but with respect to the real-time data sets, we need to have the clear, solution for the adaptive sampling algorithms as well as the storage driven solution. That's when we just went with the hybrid solution called the Apache in memory computing with the IO integration. So in future, right now we just tested out with the NWChem molecular dynamic data set, and then we would like to go with the even bigger, larger data set called the OCP data set, Open Catalyst data set, and then we would like to evaluate our proposed to release works well or not here. So could you please move on to the next slide? Yeah, thank you so much for my collaborators in Lawrence Berkeley and the UT Dallas, as well as the Dewey Oscar Farr Award and the NERSC Award under this project. Thank you. Sorry about the inconvenience in between. Yeah.
Let's thank our speaker. Are there any questions from the audience? Yes.
Thank you for your talk. So, although it was running on a single node, so it's a little bit hard to ask the question of scale and issues on the memory overhead when you're running simulation and the file system both on memory. But I want to ask about the comparison. There is also the high performance IDEOS library that allows you to do I/O in high speed and actually hide most of the issues of the file system behind it. Have you tried also to investigate that, or you're planning to investigate that versus your?
Yeah, thank you so much for this wonderful question. Yeah, you are talking about the IDEOS, right? MPA45 IDEOS.
Yeah.
Yes, we tested out. Yeah, in the next project, we already established the multi-node with along with the MPI and then IDEOS. Yes, we tested.
Okay.
We have time for one more question if there are questions. No. All right, let's thank our speaker one more time.
Okay, thank you so much.